Okay, so last time we did an introduction to random variables. We talked about random variables as a continuation of probability. So this unit is going to be pretty closely related to last unit. We talked about just in general what is a random variable. We looked at discrete versus continuous. Today we are mostly going to focus on discrete. We're going to calculate the mean and we're going to calculate the standard deviation. We'll take a look at a little bit of continuous. Few other things for us to know. Today, we're going to talk about calculator. So you're going to learn how to do the mean and standard deviation on your calculator. And we're also going to learn some of the formulas that are on your formula sheet. So what we're doing today relates to these formulas. Little bit of review of what we talked about last time and what we just went over in the warm-up. Random variable takes on numeric values only. We took a look at what is a discrete random variable, and then we'll take a look at discrete and continuous today. We are going to start out with this example. So this is the page that I want us on. So one wager that players can make in roulette is called a corner bet. To make this bet, a player places his or her chips on the intersection of four numbered squares on the roulette table. If one of the numbers comes up on the wheel and the player bet $1, the player gets his or her dollar back plus $8 more. Otherwise, the casino keeps the original $1 bet. X is the net gain from a single $1 corner bet. Therefore, the only options are the person lost $1 or gained $8. The table shows those two possibilities and then their probabilities. We talked about this last time. How do we know that this is a valid probability model or a valid distribution? Okay, probabilities have to add to 1. So what we're going to talk about today that's new is average. So let's say a player sat at the table and played this game over and over and over again for 5 hours. What would be the average gain? Okay, so looking at our probabilities, we see that both of them have a denominator of 38. So let's imagine that the player played this game 38 times. If this were a perfect world, then the player would lose $1 34 times and then win $8 4 times. And then we would have to divide, of course, by the 38 games. Now, is this likely what's going to happen? No. This is what we would expect in a perfect world, but it's not likely to be exactly what happens. So if I'm going to write this a little more efficiently, there are 34 of those negative 1s and 4 of the 8s. And then taking it one step further, this is the same as 34 out of 38 times negative 1 and 4 out of 38 times 8. And so if you do that calculation, the mean ends up being negative 5 cents. Forgot my dollar sign. Negative 5 cents. What does it mean that the mean is negative? On average, we're expecting the player to lose. So if I asked us to interpret this, we would say something like, in the long run, if a player played this game many times, he or she would be expected to lose 5 cents per game on average. Okay, what I want you to notice is I did not put negative in my interpretation. I didn't need to because I put the word lose. So the negative should not be in the interpretation. The other thing I want to point out to you is that this is what is expected. Expected to happen on average. Now, can a player play a single game and lose 5 cents? Is that possible? No. You should not be rounding this, though. This is a long run average, so we're not rounding. Now, we are going to use this idea to come up with the formula. So if we want to generalize, what is this formula? Well, what did we do? 34 out of 38 and 4 out of 38 are the probabilities, and -1 and 8 are the values. So what we did is we took each value of x, we multiplied by its probability, and then we summed them all up. So is this formula on the formula sheet? Yes, it is. The only difference is there's normally a little I here, just to denote that there are different x values. That's all it denotes. When you are interpreting, one thing to say, expected value is the same thing as mean. So if you are asked to calculate the expected value, that's the mean. Okay, interpreting. In this blue interpretation up here, what do you think are the words that I'm looking for? Words, phrases, ideas. Long run.
Many times.
Many times. Expected. So these are the things that I am going to be looking for anytime that you are interpreting. Okay, so what you are going to do now is you are going to calculate and interpret the example that we did on the previous page, which I think I have that table. So it's this one. So with the person next to you, what I want you guys to do is looking at this table, calculate the mean, and interpret the mean, showing work. Okay, let's start talking. Question over here was, do you need to show your work? You do. You need to at least show the first multiplication, so 1 times that 0.630, plus ... all the way to the last one. So 5 times 0.002. And I got the mean to be 1.457. You guys agree? Mm-hmm. Okay, so then contextually make sure that that makes sense. Our data is people speak between 1 and 5 languages. Does it make sense to have an average of about 1.5? Yes. Okay, so then if we interpreted, we would say something like, in the long run, if we sampled many U.S. high school students, the average number of languages spoken would be 1.457 languages. So I guess above I should have said expected/average. You're using whichever term makes sense. Saying we expect 1.457 languages doesn't really make sense. And then this question we already answered. Does the expected value have to be equal to one of the possible values? So is there an issue that you can't speak 1.5 languages? No. You just leave it like that. On the AP test, if you were to find this value and then round it to 1 or round it to 2, you will get the question wrong. So the AP test is very picky about that. Questions on that? Correct. If we do mean, what else do you think we're going to do? Standard deviation. Yeah, we are. Let's talk about standard deviation. Okay, I'm going to tell you, this formula is a bit of a doozy. First thing to remind us of is in order to find standard deviation, which is sigma, we always have to find variance first, which is sigma squared. Okay, so to find variance, what you're going to do is you will take every x value, subtract the mean, and square it. Then you will multiply by the associated probability and sum them all up. And then, of course, to find standard deviation, you'll have to take the square root. Before we find standard deviation, let's talk real quick about interpreting it. If you interpret standard deviation, it is the average distance. The outcomes are from the mean in a large number of trials. So for example, if we did this for the languages example, the average is about 1.5. I'm just going to call it 1.5 because it's simpler for my calculations. If I took you all as my random sample, and I went around and I asked every one of you, how many languages do you speak? How many languages do you speak? One. So the average between Lily then, or the distance between Lily and the average is negative 0.5. Mikey? 1. So again, the average is negative 0.5. Daniel? 2. So the average is 0.5. If I found all of those, and for my negatives I made them positive, and I averaged them out, that would be the standard deviation. Does that make sense? Do we remember why I have to consider the negatives as positive values?
It's like you can't look at negative, or I don't know, it's like distance from the mean.
Like, it's either like positive is above the line and negative is below the line. Like if
Right.
you're making it a reciprocal.
Let's get to doing the calculation and then see if my question makes a little more sense. Calculate and interpret the standard deviation from the languages example. So I'm going to bring up that table again. We're going to do this one together. Okay, we already calculated the mean. So we already know the mean of this data set is 1.457. Okay, so if we go to find the variance, what we're going to do, we're going to take the first x value of 1, we're going to subtract the mean and square it, and then we'll multiply by the probability of 0.630. You're going to have to do that for every x value. So then our next x value is 2. We subtract the mean, square it, multiply by the probability. Then we'll take the next x value of 3, square it, multiply by the probability. And you would do it for all 5 of the x values. So that would give us a variance then of 0.450. And the units are squared. So this is languages squared, which doesn't really make sense. And so what we do instead then to get something that does make sense is we take a square root. So our standard deviation is about 0.671 languages. Can we agree that this is a pretty tedious process? If we were to interpret this, we would say in the long run, if we sampled many U.S. high school students, the number of languages spoken would typically deviate by 0.671 languages from the mean or average. Okay, so I asked us before, when we have our differences here, some are positive, some are negative, why would I make all of them positive before I took the average? Looking here, do you wonder why we square everything and then take a square root? Right? If they're going to undo each other, why bother? Do you remember why we have to square? When we calculated standard deviation before, we had to do the same thing. We had to square and then take a square root.
So we have positives only. So it's like
Okay, why does it matter that we have positives only?
the standard deviation standardized? That's like,
It's not standardized. It follows the units.
Because you're adding them all up, so if you have positives and negatives from the start, they would like balance each other out and make it seem like they're not really deviating at all instead of that they're.
Does that make sense? If we have positives and negatives, they're going to cancel each other out. And in fact, beyond that, you would get a sum of 0 every single time. So that's why we end up having a square. Okay, you should be thinking right now, man, this is pretty tedious. I wish we could do this on the calculator. Aren't you? Let's do it on the calculator. Okay, so what you're going to do in the calculator, you always have to give the calculator your data. So we're going to use the languages data. Do you remember where to go in the calculator to put data in? Stat. So right now, you're going to go to stat. You're going to go to edit. You're going to put the number of languages in list 1. And you're going to put the probabilities in list 2. So put the number of languages in list 1. Put their associated probabilities in list 2. Okay, so once you have your data in list 1 and list 2, quit out. Where did we go in the calculator before to calculate mean and standard deviation? Stat, calc. So you're going to go to stat, you're going to go to calc, and I'll pull up the calculator in a minute so that you can see me do it. And then you have 1 var stats and you have 2 var stats. And this is where people tend to go wrong. 1 var stats is 1 variable, 2 var stats is 2 variable. So I think it makes most sense to say, well, we have 2 lists, so we must have 2 variables. That's not the case, though. The only variable we have is number of languages spoken. So you're going to do 1 var stats. Okay, so you're going to do the 1 var stats like we just did. You're going to do L1, which is where your data is, and list 2, which is where your probabilities are. Here's what I need us to know about using the calculator. 1 is that you must show your work. And it's like I said, show the first substitution, the last substitution, ... in the middle. But you cannot just pull the mean off of the calculator. Second thing I need us to recall. There are 2 different standard deviations that your calculator gives you, S of x and sigma of x. The first thing that I want to remind us of is what the difference is. What does S stand for versus sigma? Well, they're both standard deviations.
No, the S is for the population, and the other one's for the
Just the Y, right?
or
Flip.
the other way around.
Other way around. So sigma is the population standard deviation, and S is the sample standard deviation. Did you guys notice when we just did this, the S was blank, and it only gave you a value of sigma? Okay, in the beginning of the year, when we did standard deviation, I told you, you always use S. So you have to remember, normally you're using S. The only time you use sigma on the calculator is when you don't have an S. So I need us to remember that if I just gave us 5 numbers and said, find the standard deviation, you're using S. The only time you don't use S is when you don't have it. We've talked a whole lot about discrete random variables. We need to touch on continuous very quickly. We're not going to do a lot of continuous variables because much of the calculations behind continuous variables involves calculus. This is not a calculus-based class. So, first thing we should probably talk about what is a continuous random variable and give some examples. We've already talked about this. A continuous variable can take on any value within an interval on a number line. So the two variables that we looked at in the beginning is I might ask you your shoe size. Oh my gosh, I'm having a lot of trouble spelling. I could ask you your shoe size. I could ask you the length of your foot. Now, shoe size, we said you could be an 8, you could be an 8.5. Your shoe size cannot be an 8.7 though. So shoe size, we said, is discrete. Foot length, though, can be anywhere between, 1 inch and 40 inches. That's continuous, not 1 and 40, but a reasonable interval. Okay, is it possible to have a shoe size that is exactly equal to 8? Well, yes. Is it possible to have a foot length that is exactly equal to 8? Not really. If it were equal to 8, that really would be like 8.000005. Now, how many different foot lengths are there? There are infinitely many. So the question is, how do we graph them? When we looked at number of languages, which was discrete, we graphed that using a histogram. How do you graph, though, a continuous variable like foot length using a histogram? Well, we could do 8 inches to 9 inches, 9 inches to 10 inches. We could put them in intervals. Instead, what we do is we graph a histogram with really skinny rectangles. And if we make them skinny enough, there will be infinitely many of them. And what happens then is it looks like a curve. So you've seen that before, a normal curve. A normal curve is the graph for a continuous variable. So you picture, you have all these rectangles, these intervals, you make them really, really skinny, it'll give you a curve. So then, how do you find probabilities? When we have a histogram, we just look at our intervals. When we have a curve, what we're calculating is area. Keeping in mind the area underneath the curve is 1. Okay, so let's look at our two variables again. We looked at shoe size, which we said is discrete, and then foot length, which we said is continuous. For either of these, I want to compare what is the probability that x is less than some value, like 8, and the probability that x is less than or equal to some value, like 8. If we look at shoe size, is the probability that x is less than 8 the same as less than or equal to 8? If we're thinking of shoe size. Are these two the same? No? Right? This includes a shoe size of 8, that one doesn't. That's the case for any discrete variables. So anytime your variable is discrete, whether or not we include something matters. Now, if it's continuous instead, like foot length, now a probability is an area. And so the question is, does the area change if we include the boundary? No. So this is really big. For a continuous variable, it doesn't matter if we include the boundary because we are looking at area. Mm-hmm.
Is that also because like there will never be a point at exactly 8?
Yeah, but theoretically, if there could be even,
It'd still be equal.
wouldn't really matter. Yeah. Okay, we've got one last problem to do, and this is really a review. It's a review of normal distributions because that's the only real continuous variable that we're going to look at. The weights of 3-year-old females closely follow a normal distribution with a mean of 30.7 and a standard deviation of 3.6. Randomly choose one 3-year-old female and call her weight X. Okay, before we even do part A, the very first thing that we have to do is say that X is normal with a mean of 30.7 and a standard deviation of 3.6. As I've said before, that's really repetitive. You still have to show it. Even though that says so in the problem, you got to show it. And then anytime we have a normal distribution, of course, we're going to draw a normal curve. So you're going to label symbols, the mean, standard deviation, one standard deviation below. And then you're going to use the numbers from the problem. So this is 30.7 and about 27.1. And I'm not going to label anymore because I don't want to have to do the addition in my head because I don't trust myself. So that's all before we even got to part A. So now, if we get to part A, find the probability that the randomly selected 3-year-old female weighs at least 30 pounds. So probability of at least 30 pounds. So on the figure, we would mark where 30 is, and then we would shade. How do we do this on the calculator? Normal CDF. You don't need to write normal CDF. I'm just writing it because it's your notes. Lower bound is 30. Upper bound is some big number. The mean is 30.7, and the standard deviation is 3.6. And if you trust me, I will say you get about 0.577. Make sure that makes sense. So if the entire figure is 1, does it look like we shaded about 57% of it? Yes. So that checks out. The other thing I want to remind you of is that if you were asked to interpret this, it's a long run. You'd say something like, in the long run, if we selected many 3-year-old females, about 57.7% of them would weigh at least 30 pounds. Okay, I will tell you, the book uses z-scores. I don't see any reason to do that. So what the book will do is the book will take that 30 and convert it to a z-score and then use normal CDF. Well, you don't need to do that, so why bother? So I'm telling you, this is not necessary. Some of you like to look in the back of the book and then copy it down because you get so nervous. You don't have to do that. As long as you have this normal statement in blue, you're covered. And then just use your calculator. If you want to convert to a z-score, go for it. I think it's a waste of your time. Last thing, we're going to do C. Find the probability that x is less than k. Oh, if the probability that x is less than k is 0.8, find the value of k. Okay, so k is somewhere here. I don't know where, but it's somewhere there. And all the area below it has to be 0.8. And that's what I expect. Shade, show me the area is 0.8. How would we do this on the calculator? Inverse norm. So this one we're going to do inverse norm. Area is 0.8. The mean is 30.7. Standard deviation 3.6. Now, I will tell you, when I initially did this problem, I got an answer of 27.67 pounds. And if you saw my answer, what would you say to me? It's incorrect?
Doesn't make sense.
Why does it not make sense?
Wait, never mind. I was looking at it for a different.
Okay. So you guys are, trust me? Yeah, that's good? You should be telling me it doesn't make sense.
It doesn't line up with your graph, with the shading.
Yeah. Does it make sense that I would get a value below the mean? Definitely not. So again, that's why you're doing the graph. I didn't check my graph. I just looked at that answer and said, yeah, it looks good. It's not, it doesn't make sense. So instead, I will tell you, when I did it again, I got 33.73 pounds. Does that make more sense based on the figure? Yeah, it should. Okay, that's our notes. Do you have questions for me?